So these are the possible fusion. Deuterium plus deuterium to give us tritium plus hydrogen 1 plus huge amounts. Deuterium, two deuterium fused together to produce this. Are we together? So plus huge amount of energy, where Q is the energy release as a result of the reaction. If Q is equal to 4.0 MeV, calculate the atomic mass of hydrogen tritium in AMU. So we are given deuterium and we are given, we used to call this proton because it's charge of 1 and mass of 1. So we are given this hydrogen 2 equals to this. So now how do you find this? Now you have deuterium plus deuterium to give us tritium plus this plus Q. Now the deuterium, we are given the atomic mass unit. So here you have 2.001410 plus another deuterium. We are given the atomic mass unit 2.01, okay, is 01, sorry, 2.01410. Now tritium, that's what we are looking for. Yeah, we have to find that of tritium. So let's call it X plus. We are given that of proton, this hydrogen 1 as, yeah, that's actually proton plus 1.00783. Are we together? Plus, don't forget we are given Q2. We are going to add that of Q to it, and our Q is equal to 4.03 MeV. So you are going to convert that MeV to U. You can't just add it like that. No, here we are told that 1 U equals to 931 MeV. So what will be, how many U with 4.03 MeV be equal to? This is it. If 1 U equals to 931 MeV, then how many U, XU, will be equal to 4.03 MeV? Cross multiply to get your X. So 4.03 times 1 will be equal to X times this. Are we together? Then X will give you 4.03 times 1 divided by 931. Just cross multiply and find your S. So 4.03 divided by 931. So this guy now is equal to 0.0044286 U. That's the U now. So just add this, then find your X. So if you add these two together, you get 4.02820 to give us X plus. Add these two together, what do you have? Plus 1.00783. So this one give S plus 1.01216. Then make S the set of the formula. S give you 4.02820 minus 1.01216. So you get 4.02820 minus this. So you get your X equals to your X for that deuterium tritium equals to 3.016 U. So that's that for that. And they can ask you to convert it to MeV. It's very easy. This M is capital M, sorry, it's capital mega, not milli. If it's small letter, it will be milli. Mega electron volts. So if you want to convert this guy to MeV, are we together? It's going, since 1 U equals to 931 MeV, then 3.016 U will be what? 3.016 times 931. Then you get it in MeV. So that's that for that. Now, fusion, adding, see, another thing you need to take note, whenever you see a particular radioactive question and it's called fusion, like they state there that is fusion and they fuse two elements together, and maybe you are being told that if this fuse with this, then what will be the product? Sure you get. So just calculate the mass of whatever you have here. Make sure that it's equal to the mass of whatever you have here. All those A, Z, Z, I don't have time for them now, just listing. Either A minus Z or whatever. A stands for Z mass, Z stands for proton. Leave that for now. Just listen to this. This is 3 plus 1, 4. This is 2 plus 2, 4. Both sides are equal. Let's find the proton or the atomic number now. 1 plus 1, 2. 1 plus 1, 2. So those sides are equal. So this is very correct. So if I'm having 2 here now, it's not correct. So something have to be added. That's what you just need to take note. I'm not even talking of this calculation now. Probably if I'm given something like maybe a pen 5, 3 plus an eraser 7, 4 to give me um maybe a calculator 2, 2, 4. Maybe that calculator is an alien now. And a a cleaner a cleaner 5, 8 plus q. Now, how will I know that this guy is correct? You can see 3 plus 4, that's 7. 2 plus 5, that's 7. So the downward is balanced. 5 plus 7, that's 12. 4 plus 8, that's 12, is balanced. And sometimes they can give me x here. X. So how will I find the number of proton? Just say 3 plus 4 equals to x plus 5. Then find your x. You get it to 7 equals to x plus 5. X equals to 7 minus 5. You get your 2 there. So those are the simple things you need to know, that you don't even need to be cramming some aspects. Nevertheless, we have some radioactive element that even this side will be equal to this side, but there are specific elements they decay to. You have to take note of that. Read those on your slide. There are specific elements they decay to. So I can't just have uranium decaying to hydrogen and calcium. It's not possible. Sure, you get. Uranium doesn't decay to that. Uranium can have it decay to maybe barium or krypton, if I'm not mistaken, all those kind of one. So, and they may put a number on top of the hydrogen and you calculate it, you realize that it's balanced. So just note those things, please. So it's not just to have it balanced now, but those balance on, just get it now. And also you have to take note of a particular element decay to. Like, do you get? So though you don't need to cram them, but you will not be confused when you see question. There is nothing to be confused about. Just read, understand what I'm doing now, then read your slide. You are good to go. The slide is just 44 pages for nuclear chemistry. There is nothing there. Read your slide, you are good to go. Now that's that for fusion. Now for fission, whereby we'll be having elements splitting into two. You can also have calculation related to that on this. So for fission now, so we've discussed fission, but for fission now you can have something like whereby you have an heavy nucleus splitting into two light nuclei with release amount of energy. And please, for fusion, it's not just the release amount of energy, is with the release amount of huge amount of energy and neutron. Fission will always yield neutron, and not just neutron. Approximately 3 neutron. Take note of that. You know neutron is n0, n01. But for fission, it will yield approximately 3 neutron. So whenever they are mentioning fission and you don't see neutron as the product, I don't think that's correct. Because for every fission, we have approximately 3 neutron released. It's in your slide too. Are we together? So now let's see the fission of uranium. Maybe it occurs with a slow neutron. Fission occurs with a slow neutron, maybe plus uranium 235 to give us, don't forget, this will always be there, plus q. That q either is energy or q you see there, so they are the same thing. So to give us barium 56 plus krypton 36, with atomic mass of 92. This one is 144 and this guy is 92. Is it 92 now or 89 rather? 89. Yeah, some textbook they put 92 here, they put 141 here. There's no problem about that. Just calculate all your masses here. The mass we have here for neutron is 1. 1 times 3, that's 3 mass already. For the proton, for the atomic number, the proton, 0 times 3 is 0. For the mass is 3. 3 plus 89, that's 92. 92 plus 144, that's 236, abi. Let's find the mass here. 1 plus 236, that's 236. The mass is balanced. Now let's find the proton. Is 0 plus 92 here? 92. 56 plus 36, 92. Plus 3 times 0 is still 92. So the proton is balanced. You can see uranium, undergoing fission with a slow neutron to give barium and krypton with the release amount of high amount of energy and neutron. Take note of that. Whenever you have fission, neutron is always released. So not just what's it called now? Not just not just uranium that undergo fission, many other elements. So I've done fission, but let me just do one more on fusion. This fission now, fusion now, that one that we combine together. So take for instance, we also have hydrogen, deuterium, and tritium. And they can tell you a deuterium combined with a tritium to why a neutron and high amount of energy is produced, then what would be the element? How can I put it now? Maybe okay, a deuterium joined together. I'm talking of fusion now. This one is fission. Now for fusion, I just want to do one more example. Like a deuterium joined together with a tritium. Are we together with a tritium to produce element X? Let me put it that way. I'm just trying to, code a question to produce element X with a neutron. Yeah, I think that one is good now. Plus Q, high amount of energy. Yeah, this is good now. Find element X. You can have your question like this. What is the element X? So this is just find what's the total mass you have here? 5. What do you have here? 1. That means the element that is here, the mass will be what? 4. No, this is 5. 5. Here also you must have total number of 5. Since you already have 1, the mass of element here will be 4. Those A minus Z, just leave that. Just listen to this one. All those on that A, Z, all those on, leave that. Listen. 2 plus 3. That's 5. Here you have 1. What do you need more to make it up to 5 on this side? 4. So now find the proton. 1 plus 1, 2. Here you have 0. That means you must have 2 here. So the element X has mass of 4, proton of 2. That should be what? Helium. Are we together? That's our element X. That's that for that. So now let's move to transmutation. Transmutation now. Transmutation. When we're talking of transmutation, that's when we'll be talking of artificial bombardment, artificial radioactivity. Are we together? So what is artificial radioactivity? This is just a phenomenon in which ordinary material, that are not radioactive. Originally, they are not radioactive, but we make them a radioactive substance by bombarding them with something like maybe we bombard them with alpha particle, neutron, deuterium, whatsoever, by bombarding them with elements. They are not radioactive. Now, radioactive element that are radioactive naturally, according to the slide, I think they said the atomic number is greater than equal to 82. Yeah. The one in my secondary school is greater than equal to 83. But according to the slide, I think they use 82. So any element that is below 82 is not a radioactive element naturally. Yeah. But you can bombard them with some things to just make them undergo radioactivity, which we can say that's artificial radioactivity. Do you get that for that? Now, when we have like a nitrogen, it's not a radioactive element, but we want to let them to undergo such reaction, such nuclear reaction. This 7, like nitrogen, that's just an example. Maybe you bombard it with alpha particle, helium. Are we together? To give oxygen. Maybe okay, they told you when you bombard nitrogen with helium and a proton is produced plus energy with an element Y. Find the element Y. Find the element. Why? You know how to do it. Calculate all the, what's the mass here? 14 plus 4, that's 18. So here you have 1. That means the element there will be, the mass there will be 17. 7 plus 2, that's 9. Here you have 1. That means here will be, so that's oxygen. No, oxygen, you say the mass is 16, fine, but the proton will determine the element you are talking about, not the mass now. We have isotope of oxygen. This is another oxygen. We have oxygen 816, we have 817 too. So the number here will determine the element. Don't look at this thing. It's possible you have 18 yourself, but don't look at that. Just look at the proton number. We determine the element. Are we together? So that's that for that. We also have so, and then whenever you see some, they can give you something like this. They can say which type of radioactivity does this thing which type of radioactivity occur here. This artificial radioactivity. Any element that the atomic number is less than 82 is artificial radioactivity. Are we together? It's artificial radioactivity, but I don't think they can ask you that. Well, they can actually. So we don't have much time. And we also have decay. Decay, you can read that in your slide. Now, moving to radioactive emission. Radioactive, radioactive emission. And we're talking of emission. There are 4 types of emission. We have the alpha particle, we have the beta, we have the alpha particle, we have the beta particle, we have the beta particle. Yeah, I want to do something, sorry. We have the alpha particle emission, we have the beta particle emission, and we have the gamma radiation, gamma emission, gamma radiation. These two, they are particle, while gamma is not a particle, it's a radiation. Well, I don't think I see that in the slide. That's just for my secondary school notes. So now, this beta is into 2. We have the minus and the alpha particle, usually helium. This alpha particle, usually helium. Beta particle, we call one electron, and we call the other one positron. Whether they don't call it electron, just know beta particle, we have a what is it now? Yeah, a 0 mass with -1 charge. Yeah, this a beta particle. One beta particle is in 2. This one, the other one, let's call this beta 1, beta 2, can also emit 0 plus 1. This is the second beta particle. This one is positron. This one is electron. Are we together? Beta particle emit, there are 2. The one with -1 charge, the one with +1 charge, but both have 0 this thing. So this is just like you guys, we did this thing in physics 102 for those who did physics 102. So beta part, for the beta particle is just like the beta and the anti-beta. Sure, you get the beta and the anti. We have all those particle and antiparticle. So this a particle and the anti-particle, the same mass, equal but opposite charge. So that's for beta particle. Now the last one is the gamma radiation. That's 0 mass, 0 charge. So whenever you are told that so kinikon undergo a radioactive kinikon and emit 4, okay, maybe we are being told that this guy maybe an element P with atomic number of 84 and mass number of 206. I don't know if an element exists like that with mass number of 206 and atomic number of 84, but just listening to my explanation. Undergo a radioactive decay. By emitting 4 alpha particle. Then what will be the product of the element that we have left? The element we have left, this does it, 4 alpha particle. Are we together? Just know there will be plus Q. Don't forget, plus Q will be there. So now, here we have 4 times 2 for the proton. 4 times 2, that's 8, right? And this 84 proton. 4 times 2, 8. 84 minus 8, we should have 76. So the proton here will be what? 76. Are we together? Yeah, now I'm not talking about fusion or fission. I'm not talking about this one splitting into two. It's just decaying, like by emitting particles. Am I communicating? So, do you get what I'm saying? That like radioactive emission. Yeah, I'm not talking of maybe splitting into two. It emits this. It doesn't split. It doesn't split to give this and helium. It emits helium. So know the difference between when it's splitting into two and when it's emitting radiation. This a radioactive. This like an emission. Are we together? So that's that for that. Here we have 76. So this 4 times 4, that's 16. 206 minus 16, you have 190 here. So maybe the element is Y. I don't know. So that's how you just have to get your this stuff. So now it can also emit, they can say it emits 3 alpha particle with 1 gamma. If it emits gamma particle, it doesn't affect, it's still 0 0. If this emit 4 alpha particle with 3 gamma particle, I will still have 190 and 76 because gamma, even though it's 1 million gamma, is 0 0. Sure you get. I'll still have it. Gamma radiation rather. Now let's move to band of stability. Band of stability. Is it proton to neutron now or neutron to proton? Please let me confirm. Yeah, I think that's neutron to proton. Yeah, neutron to proton ratio. Yeah. So how do you know that a particular element is stable? Whenever its neutron to proton ratio is equal to 1, stable is stable. Or when its neutron to proton ratio is between the range of 1.2 to 1.5. If it is less than 1.2, if it is greater than 1 and less than 1.2, it's still stable. Like when you have 1.2 to 1.5, it's also stable. But when it's beyond 1.5, it's no longer stable. When it's less than 1, it's not. This is just when you have neutron to proton ratio to be equal to 1, stable. Or greater than 1, but not greater than 1.5, is also stable. For example, let's check if oxygen is stable. Oxygen O 816. Now the proton here, our proton is 8. Our neutron, no, neutron is equal to mass plus mass. The mass equals to neutron plus proton. Mass equals to proton plus neutron, and our mass is 16. Since our proton is 8, our neutron will be 8 too. So our neutron to proton ratio 8 over 8, which is 1. So this oxygen is very, very stable. Are we together? So anyone you should just do, for instance, uranium 235, uranium 92, 235. So the proton here equals to 92. Why the neutron? The neutron will be the mass minus the proton. 235 minus 92. That's 235 minus 92. That's so the proton, the neutron equals to 143. So the neutron to proton ratio will give us 143 over 92. 143 divided by 92. That's 1.55. So this guy is not stable. It's greater than 1.5. It's not stable at all. That's why it will continue emitting um radioactive emission. So it's not stable. Unstable nuclei is unstable at all. Am I communicating? So most of the element, or even if not all, yeah, or let me say most of the elements that have the atomic number greater than 82 or 83, they are unstable. That's why they call them radioactive elements. So like they are most of them, they are not stable. They keep on emitting radioactive emission. So that's that for that. I won't do much on that. Now the last thing I'll be doing now is magic number. Magic number. Please note this number 2, 8, 20, 28, 50, 82, 126. I think I'm right. Yeah, I think that should be magic number. 2, 8, 20, 28, 50, 82, 126. Yeah, that's right. That's right. So these are the to know elements that are stable. These are the magic number. Just cram this thing, cram them. So there's no formula to know them. Cram them. So any element that have some element have single magic number, they are stable, no. But those ones that are very stable are those ones with double magic number. For oxygen, oxygen has an atomic number which is proton number of 8, mass number of 16. Oxygen proton number is 8 and the neutron is also 8. And out of the magic number, among the magic number, 8 is part of them. So an oxygen proton is 8, neutron is also 8. That's double magic number. We have 8 among the magic number. So oxygen have double magic number, very stable element. Do you get? Very stable. We also have this guy too. Um is it lead? Yeah, lead. Lead is gallium, lead, bismuth, polonium, astatine. I think lead is in number 82. To that in uranium. Yeah, lead is number 82. Yes, with atomic mass of 204, if I'm not mistaken. I will know now. 204 minus 82. 204 minus 82. Oh, 208 rather, yeah. Lead is 208. Sorry for that. So the proton number of lead, P equals to 82. Why the neutron, that's 208 minus 82. Mass minus proton, that is 126. So lead is very stable. Lead is also stable. Lead is stable. Are we together? Lead is stable. So because it has two magic number, 82 and 126. Are we together? The proton and the neutron are the one we are considering as those who contain the magic number. Is once your proton is equal to the number you have in the magic number and your neutron too, that's double magic number. Because this magic number, just know it. I think the next one should be 184. But for now, I think this is what is in your slide. 82, it has it. The proton has a magic number. These are the magic number you need to know offhand. Let's talk about calcium too. Calcium 20 with atomic mass 40. So calcium proton equals to 20. The neutron too will now be what, 20 because the mass is 40. So proton has double magic number. This is it, 2020. So that's that for that. Please, what I've taught you, just learn them and don't just depend on them. That's why I told, though we've not done chemistry, we will do chemistry by God grace. Yes, chemistry tutorial physically. That's why I told those who came for phys 102 lesson yesterday, like, come for the lesson. There are things I will say in the lesson I won't be able to do in the video. This video is just like a brief, like just trying to touch every aspect. We'll not be saying everything here. Come to the physical lesson, please. And it's free. It's free. More than 50 students came yesterday, whereas we have much more than them that did not come. They are waiting for video. I pity you. Good. Okay, goodbye. See you guys later. I love you.